Can you hear me now? Maybe there's no sound. Maybe talk. Testing. Yes. Okay. So test. Okay. Maybe Felix try to speak.
1 2 1 2.
Can you guys hear Felix?
Hello, hello.
Yes.
Nice, Manu.
All right.
So far, two viewers that I think both know. Okay, great.
Cool. Well, one thing, Felix. Can you click on the hide for the share screen on the bottom? Yeah. Perfect. Cool. Well, thank you everyone for joining us. And today we have Felix Lupo, who's the CTO at CoW Protocol, and we also have MFW78, who is the technical reviewer and grants committee for the CoW grants program. And they're gonna talk about composable CoW architecture, this new framework actually developed by the CoW grants program and by MFW itself. And with this, I pass on the mic to them to educate you on how awesome these features are.
Yeah, let's maybe start just with a quick. Thanks for the intro, Alex, and just a quick, kind of a little bit more context of what we're trying to do in the next hour or so. Is first, let's start talking a little bit about smart orders and kind of what this principle of smart orders is. We'll do a very quick demo of how a regular order looks like and how it compares to smart orders. And then we'll dive into the hand over to MFW to explain a little bit more the framework that he built that really enabled smart orders on top of formerly doses, now just safe, as a paradigm to basically express arbitrarily complex trading strategies that you might that you would like your smart contract or even your EOA managed by a smart contract to execute. And then we'll dive into VS Code and go a little bit through the framework that MFW built and actually go and hack a new order type ourselves. So the framework already comes with some special orders, good after time. What is this? Oh, stop loss is in there. Did you? Well, I guess I'll just delete it because this is what we're actually trying to build. And yeah, then hopefully you will deploy it and have an end-to-end demo with everything working as expected. MFW, do you want to add anything about maybe your background, how you got into CoW, what excites you about the space, and yeah.
Sure. So I've been an active member of the community from my XDI chain days, and then obviously with the Gnosis buyout of stake, then got me further into the Gnosis ecosystem, and by extension of that, CoW protocol. I'm particularly attracted to the idea of solvers and the solver auction mechanism and how that can be applied both in terms of the ERC20 paradigm, but also more broadly as well in the future as a meter construct. And yeah, so basically in terms of the composable CoW architecture, I designed this mostly as a need for my own treasury management to maintain a certain level of USDC runway and automatically trading. And that's what gave birth to this.
Awesome. Cool. So let's maybe dive into the concept of smart orders and what we can do before we actually see what smart orders are. We can just look into how a regular order works. Most of the viewers have probably seen CoW, but it's so big. But basically, if you're trading on CoW, I have a fresh account here for this session, so I'm not making any stupid mistakes. So I probably need to grab some width first. But basically, the general idea of CoW's orders is based on off-chain signature, basically trade intents that the user signs off and hands to a third party, the CoW protocol, which is under the hood powered by even more third parties, the so-called solvers, which then take your trade intent and try to settle it as good as they can on chain. Basically, there's this competition that compares the different ways that solvers could execute your trade, and the rules of the protocol specify that the solver that gets the best execution for the user is the one that receives the right to execute your settlement. So in the way, you have users specifying intent and getting a guarantee from the protocol that their intent is executed in the best possible way, best being expressed by price improvement or surplus. So under the hood, everything we do in CoW are limit orders. And if you're, for example, placing a limit order where you say, I want to buy Ether at $1,650, and then I'm able to get you one Ether for $1,600, I've got a $50 price improvement for you. So me as a solver, my objective value is $50. If somebody got you Ether for $16.25, their objective value would be $25. And so the protocol picks the best solution. We can see this. So now we have some WETH here. We can see this if we want to, don't we have some WETH now? Did I not just wrap? Interesting.
It's
There, so it's good now. Okay, no, it is. It was a bit slow to update. So after having set the allowance, we usually sign an order on CoW. Let's first set the allowance. I could have prepared that a little bit in advance, I guess. And so now when we click swap, what we're actually signing is not a transaction, but it's just a message. It's just the intent of an order, basically. So we have a sell token, we have a buy token, we have somebody who's receiving the funds, we have a sell amount, we have a buy amount, we have a validity, some app data there that tells us a little bit about which UI we're using, and the rest kind of, yes, it's a sell order, it's not partially fillable, there's some fee to it. And when I sign this, basically, I'm not signing a transaction, but I'm signing this intent that gets shipped off to the solver network. We hear the very rewarding cow sound. And so if we look under the hood, what is happening, how do I find out maybe I should check them. This might take some time to execute. Let's look at the last batch. Let's look at the last batch on mainnet. So if we look at the last mainnet batch, for example, here, we have one user trading Prime for USDT. And if we want to see under the hood what is happening, here's my happy moo sound. We can see that, basically, let's look at the invocation flow when it loads. Could use Tenderly for this as well, maybe it would be faster. But basically what we can see here is that the way that the transaction authenticates that me as a user, I'm actually willing to make this trade, is by using EC recover. So because I've signed this message using my EOA, the settlement contract is actually able to recover my signature and then validate that I am indeed willing to sell West for DAI at the limit price that I've specified. And this is basically how the smart contract makes sure that only trades that you're actually willing to execute are happening on your behalf by verifying and recovering that signature that we just made in the MetaMask browser. Now, the problem here is that signatures, real physical ESC, ESA signatures can only be executed or made by externally owned accounts, by these things that are backed by seed phrases, private keys, and not really by smart contracts. So for example, if I have a safe wallet, I am not able to create or sign a message with a private key because my safe wallet or my safe core contract doesn't have a private key. And so the Ethereum community defined a standard for this, it's EIP1271, which specifies a way of how smart contracts can also express that they are okay with a certain message, you know, and instead of like creating a cryptographic signature, they basically create a logical signature saying, I'm okay with this message being used you know, on my behalf, in my name. And really what it is implementing one single method contract, which is called isValidSignature. It takes the hash that to verify if you're okay with it. So in EC recover, that would be basically the message here. And then it takes an arbitrary byte string, maybe you see it better here, an arbitrary byte string as a signature. And it is up to the contract to then do whatever it wants to do to verify that this signature is indeed valid for this hash. So the very naive, basic way, how Safe does it by default, for example, is to assume that the signature itself is a cryptographic signature from an EOA and verify that it signs the hash and the EOA is whitelisted, for example, in the smart contract to authorize these kind of operations. But the cool thing here is that it is not necessarily required that signature is indeed an ECDSA signature from an account. It could also be any arbitrary information, and isValidSignature could implement any arbitrary on-chain logic to decide, am I willing to sign off on this hash? Yes or no. And so this is basically what we then frame more generally as smart orders. It's CoW swap trades that are authored by safes, that are authored by general smart contracts, which implement advanced logic in this isValidSignature. Basically, we have a bunch of examples in the code base that we'll see. You could have logic that checks, for example, is the current block timestamp beyond a certain point. If not, you're not willing to trade. If it is, you're willing to trade. So you could create an order that mimics a good after time order this way. Another order type that we've implemented was trade above threshold. You can say that I'm always willing, you know, I might receive my salary in USDC, but whenever my USDC balance goes above a threshold, I want to trade it for Ether, let's say, because I want my long-term savings to be in Ether. MFW worked very hard on a TWAP order type, so where basically, again, based on the current timestamp, you decide how much you're willing to trade. So over time, you're trading more and more, and you're not starting off with a lot in the beginning. And stop loss orders is another example where you might say, I want to trade if certain threshold price is reached. And then there's more advanced trading strategies that you could also implement, such as, I think we have an example of a perpetual stable swap where for example, you're saying, I value USDC and DAI 1-to-1. So I'm always willing to trade all my USDC for DAI as long as I get more DAI than I have USDC. So you basically say, you know, you can swap back and forth as long as you give me more of the other. You know, you can use them 1-for-1, and you can even implement more complex AMM designs with it, where you look at your balances, and if the change in balance that the order proposes still verifies a constant formula like x times y equals k in the Uniswap case, then you say, yes, this is a valid signature. I'm happy. And maybe just one more thing here that isValidSignature is actually already used in production on CoW swap today. You might have seen in the very beginning, I actually first wrapped WETH into Ether to do the demo, but as of somewhat recently, like 6 months ago, we have a native ETH flow where you can swap not just 20 tokens for another ERC20 tokens, but you can also swap the native currency for ERC20 tokens. And if you do that, what actually ends up happening under the hood is that you are signing, in this case, a transaction. Yeah, this is not a message. You're signing a transaction where you transfer your ETH into a intermediary contract, and that intermediary contract then places an EIP1271 order on your behalf. So let me show you how that actually looks like. If we go to the Explorer, so one person that is actually very, very heavy user of our native flow, Alec, doesn't like to be called out, but you know, we can use this as an example probably. So what we can see here is that the actual source of the funds, the actual then sent into the contract, is coming from an intermediary contract that has the ETH flow contract. And if we look at what is actually under the hood in this transaction, we can see that here in this line, we are actually invoking isValidSignature on the native ETH flow. So here's an example of, this is in the settlement contract. The settlement contract realizes that the order that was placed is an EIP1271 order. And then the way it tries to verify this order is by invoking isValidSignature of the order digest and the signature that we've given it on the owner contract. So in this case, on the native ETH flow contract. And I'm not sure if this works. isValidSignature. Can we see the code of this? So I can see it on either scan. So here, if we look at the implementation of isValidSignature, right, this is the wrong contract. isValidSignature here. And we can see the logic that the native ETH flow implements, and basically the order hash is stored inside this contract in a struct, and the basically what it does is it looks up what it has stored for this order hash inside its internal state, and then it checks that basically it hasn't been canceled, so it just trusts that basically the user has placed this order on its behalf. So all the, if the hash is the same, then all the values that the user has authorized is the same. So the only thing we need to check is that this order hasn't been canceled and doesn't have an invalid owner and is not yet expired. In that case, we return the magic value, which means it's a valid order. And otherwise we say, no, we don't want to trade this, go away. This is a bogus order. And so, yeah, basically users can tell the native ETH flow contract what they want to trade. Native ETH flow will store it, and then when settlement comes, we will look it up using ERC1271 and just in time, wrap the ETH and send the funds into the settlement contract and then back to the original recipient. So this is as much for how ERC1271 already works in production. I think now we want to go a little bit into the limitations, or why we had to build the extensible fallback handler and composable CoW framework that MFW will talk about. And really the reason here is that if we build a standalone smart contract for each individual order type, there are certain types of logic that needs to be kind of boilerplate incorporated in all of these codes and in all of these smart contracts. So if we had a TWAP contract, for example, and we would like to cancel it, there needs to be some form of cancellation logic. There needs to be some kind of logic of recovering the funds afterwards in case a trade didn't go through, because maybe the price moved in against your favor and it expired, and now the contract holds your funds and you still need to get those out. So there's a bunch of, I guess, general purpose execution logic that we would have to build into every smart order contract. And luckily, SAFE as a general purpose account abstraction tool and framework already exists and has audited and battle-proof logic that allows you to basically have full custody over the contents of a smart contract. So we decided pretty early on that we want to implement these smart orders ideally on top of a Gnosis Safe, Safe, on top of a Safe wallet, because it comes with all these non-custodial battle-tested features out of the box. And the way that you can do it is by replacing the implementation that the native Safe contracts use for ERC1271 signature verification. The basic way to do it is basically assuming that the string, the signature you're receiving here is actually a concatenated list of EOA owner signatures. And so it breaks its array into pieces and recovers the owner of each of the sub-signatures, and then increments a counter internally and checks at the end, is the counter larger than my signature threshold? So have more, if I have a 3 out of 5 safe, have at least 3 of the owners done an off-chain signature on that message, then me as a safe, I'm also fine with this message because my owner threshold has decided this is a good message. And so we can replace this logic and basically replace it with the stop loss logic with trade above threshold, what we said before. Now, the problem with that is that every safe can only have a single EIP1271 implementation. And that limit the amount of logic you can add on top of a single safe. And that's now where extensible handler and composable CoW comes in, because that really enables us on that front. And with that, I'll give it to MW to talk about it more.
Thanks for the great segue there, Felix. And so defining the problem that extensible fallback handler and composable CoW seek to remedy. Just try to share my screen now.
You want me to stop sharing on mine?
Preferably, please. And then I can use my screen if that's okay. You've got it there, Alex?
Yeah. Everyone sees your extensible safe architecture hack map.
Yes.
Okay, excellent. So as Felix brought up, let's actually go straight to some code as an example. The default safe fallback handler, currently when people instantiate safe fallback handler, a safe, it is configured using the compatibility fallback handler, which is the component that provides the is valid signature logic, which steps through the logic as Felix mentioned. So one of the problems with setting up these orders on CowSwap has been to essentially, we want to make the user experience as seamless as possible. And so we have actually been working quite closely with the safe team to develop extensible fallback handler that is able to supplement the logic of is valid signature that's currently used. So currently, is valid signature steps through and can either do an approved hash, which is the case where you have a nested safe, also a threshold signature, which is the case of concatenated EOA signatures. As mentioned, where extensible fallback handler comes in is there is a new interface defined, which is an iSafe signature verifier, which is then able to be delegated and a specific EIP712 domain separator. So what this essentially does is it creates a one-to-one relationship between the EIP712 domain and the contract instance of iSafe signature verifier, of which composable CoW implements. So this still maintains the problem of you still have a instance where you may have to create additional contracts per each order type. So this is where composable CoW seeks to essentially implement a multiplexer order flow or multiplexer order type. Actually not order type, but a multiplexer contract that is able to take essentially n conditional orders and approve them based upon internal logic. So, essentially, so now changing to composable CoW architecture. Wait a second, just checking notes. Yeah, so the extensible fallback handler, it both does the signature verification multiplexing, which is what we've had a look at here, and is what composable CoW uses. But additionally, for other non-CowSwap instances, you can also implement abstract custom handlers similar to the diamond proxy pattern. However, the safe team and us definitely don't want to use any delegate calls, so everything is stuck at call level. So that's why we've settled on this model. Safe approved. In terms of maintaining the state for where the domain verifiers are stored and authorized by the safe, that's all stored within the extensible fallback handler contract and secure using only safe. So, composable CoW go take a look at some code. So essentially, composable CoW allows a safe to define either single conditional orders, or in an advanced case, allows a safe to define a Merkle root of n-type orders. In testing, this basically, with the Merkle roots, really simple conditional order, the is valid signature will consume around 25,000 gas. When testing and scaling to say 5,000 conditional order types of relatively simple order logic, it added approximately like 20%. So you could essentially authorize up to like 5,000 different order types or different orders with a modest increase in gas consumption. So from this, it creates quite a significantly scalable solution for verifying smart orders. Whereas previous instances where we've had to create individual contracts, as Felix mentioned previously, has generally resulted in a pretty gas inefficient solution, whereas this seeks to remedy that significantly. Just checking some notes. Okay, so in regards to how this settles the order flow, so the settlement path, so GPv2 settlement, as Felix showed in the trace, makes an isValid signature or isValid signature call to the safe proxy. And then the following parts are internal to safe, where it does the delegate call to isValid signature. Then it goes through the fallback manager and calls isValid signature on the extensible fallback handler. In the extensible fallback handler, the contract that handles this is the signature verify muxer, which looks at the it checks the relationship between the safe and the EIP1271 domain. And then from that, if it finds a valid iSafe signature verifier, it will then call isValid safe signature. So the important thing at this point to emphasize is, by using extensible fallback handler, it does not change the factory or the default logic behind isValid signature on safe. So to get around this, we actually use essentially a byte for magic value prepended to the signature bytes, which is then able to signal to the contract that we should actually check if there is a iSafe signature verifier that we can delegate out to. When it does delegate out, it will go through to composable CoW, and then in composable CoW, we step through and call the verify function. So this gives just a very quick and broad overview as to how the system fits together. So the demonstration today will be we're creating a stop loss order type, but I would emphasize that people get into the Discord, have a chat to us on Tech Talk, because there's even things like being able to use like guard checks as an example to ensure that, say, like DAOs don't get spoofed or don't get tricked and change like the recipient of funds, so you can do like guard checks and like lock funds so that they can only be swapped and sent back to the originator safe. And there's a lot in here. Okay, I think that summarizes.
Cool. Yeah, just for the summary, this the last, just the HackMD. I think to me that was the most, when I first looked at the architecture. This was like the really the clarifying picture here, and it just kind of the very high level extensible fallback handler makes it so that a single safe can implement different ERC1271 logic for different domains. So CoWSwap is one of the big supporters of EIP1271, but other protocols are or will in the future as well. And so the same safe might want to have a different behavior for, let's say, snapshot voting EIP1271 as it may have for household trades. Sensible fallback handler lets you, implement different types of verifiers for different domains on your safe. And then composable CoW is what allows you to implement many different CoW orders even on the same safe. So you can have a TWAP and a stop loss and all these other kind of things, like with a Merkle root, like hundreds of different orders open at the same time on the single safe.
Thanks for the good summary.
And then let's dive into the code, right? So for the next kind of part of the session, as the MFW said, we wanna start writing some stop loss order and show how actually easy it is end to end to write new order type. And then I have a safe set up here and pre-funded on Gurley just for the session, which is a vanilla safe, so just created via the UI with the standard fallback handler, everything as it comes out of the box. And hopefully we can get to a point where we deploy our order and run it and then actually see it live. Fingers crossed. So as we mentioned before, this is the checkout of the composable CoW repository. It comes with a few order types already, and maybe let's look at how those are implemented. The simplest one is maybe good after time. And so in good after time, the idea is that you set a timestamp, and before that timestamp, the order is invalid, and after the timestamp, the order is valid. So you can say, I want to trade.
Sorry, Felix, are you sharing your screen there, please?
Oh, I'm not yet. Okay.
Yeah, correct.
Sorry.
And then maybe in the meantime, there's a question in the chat of how easy it is for a third party to have their own verifier.
For a third party to set up their own verifier using extensible fallback handler, it's quite straightforward. Obviously, they would be requesting that a safe delegates a specific EIP712 domain, and the interface is quite straightforward for implementation, and you can obviously check out the repository for composable CoW to see how composable CoW implements the iSafe signature verify interface. And I think from memory, in the safe contracts fork, there is an example test contract in there as well.
Nice. Okay. Am I sharing my screen now?
Yes, we see your code editor.
Okay, cool. Okay, so this is the code for the good after time order that I was starting to talk about. I guess the first thing we can look into is the is it the base? Yeah, the base conditional order. So basically the interface that you need to implement in order to, for your new order type, all you really have to do is subclass base conditional order and then implement even just this one method here, get tradable order. And the idea is that get tradable order should revert or not return anything as long as a contract doesn't want to trade. But as soon as your condition is matched, or whatever you want to check that makes your trade valid, so in the case of good after time, a certain timestamp is reached, then you return exactly the GPv2 order struct, which can we set in here? No, but which contains basically all information that is needed for your trade: sell token, buy token, receiver, sell amount, buy amount. This is actually everything that the protocol needs to execute your trade. And so what happens under the hood is that there is a cron job in a way, checking all the contracts that have been created, if they are willing to trade. And if they are willing to trade, it takes the order that they're exposing, puts it into the CoW protocol order book, and then it's available for solvers to pick up and match and put it on chain to then be settled. And so specifically in good after time, if we see how get tradable order is implemented, it takes the owner safe from which it is basically invoked upon. The address here, what's this address again? You might know. Oh, it's the sender. Okay, so the owner is the safe and the sender is the instance of the fallback handler, right?
The sender is the safe context. It's a safe context. So in this context, it would be the EV2 settlement contract, because that's what calls the is valid signature on the safe.
This is for verification. Okay, yeah.
Yeah, it maintains the safe calling context.
Okay, so this is the call. Okay, so settlement, I guess. Yeah. And then it has the, this would be the hash, right, that it assumes?
That's correct.
And then we have static input and we have off-chain input. And the difference here is that the static input is what is known at creation time. So for example, a good after time order, the moment I create it, I already know what is the timestamp that I wanted to check every single run. And only after that it should be accepted. Whereas the off-chain input is something that is only available at execution time, right? Correct me if I'm wrong, EIP1271.
It's available at execution time based upon what is submitted to the API. And a minor correction: the bytes 32 at the top there, just above static input, is actually the context key, which we just added recently.
I see. Yeah, this is to look something up. If you one thing that the smart contract can do is it can store, the smart order can do, it can store a value in the composable CoW framework. And this could be, we used it for TWAP to store the timestamp of order creation. This is something you don't know when you're actually signing off on the order. You know that it will hopefully be mined soon. But if you have a safe with 3 or 5 owner threshold, it might take a couple of hours before the owner signs. So the actual time that the transaction hits the chain might be much later. And if you want to have logic, like only start my TWAP whenever the transaction is mined, you need to actually have some just-in-time deployment information available. And for that, we have a storage slot for each order in the composable CoW contract, and the context key can be used to look up that context. And then, so if we look at this logic right here, basically the static input is in this case the order data. So we know at execution time, at order placement time, what the trade is that we want to do. And then the only thing that we really check here is that the current block timestamp is larger than the start time that we specified. So basically the struct that we encode here is has cell token, byte token, cell amount, has all the information we need. And then most importantly, it has the start time, which is when the order should become valid. We then also check that we have balance, just to not spam the order book if the account has no longer any balance. But interesting, and you implemented this. Is this new, the price checker?
There was an initial work towards using the price checker there, like to use Milkman, but I think this might be a different branch, perhaps a different branch, because I'm pretty sure I did pull that out prior to. Pretty sure I did pull that out prior to.
Okay.
Yeah, I thought I pulled it out. Anyways.
So, but here, it's nice to show it. It adds a little bit of complexity, but basically what we do here is we say, well, we want to trade at a certain time, but what is the price that we will accept at the time? Let's say we want to swap ETH in a month. Like, what would be the limit price you accept? And one thing you can do is you can either set large slippage tolerance and say, okay, ETH will probably trade above $1,000 in a month. So if you can get it, if you can buy ETH for, if I can sell ETH for at least $1,000, I'm fine with that. If you're maybe more paranoid that the solver competition will not actually yield you the best price, which it will, like even if in 1 month from now ETH trades still at $1,800, you will be getting $1,800, even if its slippage tolerance is very large. But if you're trading extremely large amounts, or you just have a healthy level of paranoia, you might want to add a dynamic price checker into your contract that checks at execution time. For example, what does an oracle say is the price right now? If Chainlink says the price of ETH is $1,500, then I'm not willing to accept a price that is maybe 2% below that. So you can just at execution time have additional checks. Are you fine with the order that's being proposed here, or would you rather not trade it? And so this is what this block here implements. And then at the end, very important to return the order struct. So making it so that the watchtower that is running off chain and checking with the checking if which orders want to trade knows what information to send to the backend, because this method get tradable order is actually executed twice in a way. Once when we see does the contract want to trade, and then another time when the settlement actually happens, when we are verifying that the order is correct. So there's a little bit of a double use for get tradable order, once inside verify, and once inside the watchtower that is making sure orders get sent to the order book. But okay, let's actually start writing our own order type, right? So I'm just gonna create a stop loss.sol. I should probably take some inspiration here of all this stuff, right? So what do I need? Split screen. And please let me know if I'm doing something wrong, because it's first of all my first live coding session, and I'm also haven't written Solidity code in a long time, so I might make really stupid mistakes. So this is base conditional order, and let's maybe first decide what is the struct that we want to encode our stop loss order in. So I guess we need, it's similar to actually good after time. We need a sell token and a buy token. We need, we could use a sell amount. We could also say, let's just sell everything we have. You know, the world is going under, ETH hits our, ETH is going to zero. Let's sell everything we have. Maybe that's easier. So we don't necessarily need a sell amount. We can just use the sell amount that's currently held in the contract. We can, for stop loss order, we definitely need the strike price in a way. So that would be a UN 256, right? And what else do we need? By amount, we could have a limit price. So we talked about this actually offline. If we want to build a stop loss order that has like a floor, a ceiling, where I'm willing to swap when as soon as ETH goes below, let's say $1,500, but then only until it hits 1,300. So if it goes even below 1,300, then I'm still happy to keep my ETH. So you can set a range in which you want to execute your stop loss, but it adds a bit of complexity. So maybe we don't add it here. Anything else?
We could if we use the example oracle that we have configured, the other things that could be done is if you obviously define the address for the oracle and also some other parameters around the oracle, or in this example, this could be also hard coded and not necessarily part of the data.
No, that's cool, because then we can actually use it with other oracles as well. That's a good point. So this shouldn't be an address; it should actually be an interface we define, right? And we use the interface from
Okay,
I'll just paste it in here. I guess normally you would get a Foundry dependency and then import it more properly, but this should work. Or do you have a place to put this? Maybe in interfaces?
Interfaces works okay, but generally I kept things like if it was specific to an order, which actually stop loss wouldn't be, the oracle wouldn't be, so yeah, interface can go in there for sure.
Okay, I mean, I just don't want to ruin your very clean repository.
Not as clean as it could be.
Okay, so here I also need this. Okay, and then in the, where's the stop loss? Where is it? In the stop loss, I would just import it's one up interfaces, and then aggregator. Don't I have this somewhere? But Okay. So then the oracle would be actually an instance of I aggregator v3 interface. And this should be everything we need to define a stop loss order. If we say we want to sell everything, we want to sell without a limit price, and everything else we hard code basically. Then
Yes.
the one thing we need to implement is get tradable order. I'll just copy the definition from here. So we now need to decide under what conditions and how should the trading order, how should the resulting order look like. First thing we need is we need to recover the actual instance of the stop loss order that was defined at placement time, which is pasted in here as the static input. So basically what static input is a serialized version of the data struct that we have defined here. So in a way I can take over this line here, it's the same, but it yields a different struct. It yields our struct with just these 4 values. And I guess the main thing we want to check is that the strike price is, like what the oracle is reporting as the last value is above the strike price. It's below the strike price. If it's below the strike price, then we want to trade. If it's not below the strike price, we basically want to revert.
The one thing to remember as well, like with the Chainlink interface, is there is a decimals. There is a decimals applicable to the Chainlink interface, and by default, as an example, for the ETH USD Chainlink pair or Chainlink data feed, the decimals is actually 8. Just as a heads up on that one. So for comparison of price. So for instance, if it was like, if the price reported by the oracle was equivalent to 1600 US, be 1600, then with 8 following decimal places.
I see. Okay. Do we want to account for this? I feel like we can even say, I mean, we are now using the interface from Chainlink, but theoretically you can use any oracle you'd like, a TWAP, maybe UniV3 TWAP oracle or whatever you trust. And we could even say like, well, you could even build an abstraction that implements the interface you want. So maybe for simplicity, we just assume that whatever the answer is in the latest round data is actually can be compared directly to the strike price set here.
Sure.
But yeah, that's good context if you actually want to use this in production, which of course don't. You'll probably upload a more, I think stop loss is a super useful use case, so we kind of really want to build stop loss as an order type for this, so we probably upload a more curated and polished version in the next couple of days or weeks. But for now, for this session, let's keep it simple. So data.oracle has a method latest round data, which gives us what the oracle currently thinks is the price. And so if that price is above or equal, or let's say just strictly above the strike price, and here we need to convert, right? Because it's into 56 and you into 56. So actually this guy needs.
Just on the so it's a tuple that's returned, so we'd have to break out the tuple for it.
True. So good catch. So we don't care about round ID. We care about the latest price. We don't care about the other values for now, but you could check staleness and things like that. And so this works, right? And do I have to define, how does it work? I have to define it on the...
You define it, it would be next to our latest price, define it into 256.
Okay.
Sorry. No.
Okay, let's look it up. Solidity define tuple. Nice. I'm not having any browser history either. It should be okay, but it should be.
Because I also suspect that the underscores are not needed as well.
Yeah.
Like it's just nothing. Yeah.
This is Rust. I don't even know which language I'm thinking of here, but okay.
Sure.
Latest price. Okay, so and I also made a change that the strike price is into 56, so it compares directly with the latest price we have. No need to define a strike price that cannot be expressed by the oracle. And so if the latest price is larger than the strike price, then we're okay. And we want to sell either when it goes below 1500, latest price is 1600, we're fine. So we don't want to trade, so we actually revert and say order is not valid. Is that the right revert reason, or should I use a different revert reason here if it might become valid in the future? But what's the difference between the different revert reasons?
I would have to read the documentation I wrote. But order not valid would be correct for this instance. Yeah.
Let me try to find it. Why is my auto complete not work? Very nice. I conditional order valid. Not valid. No, it's not defined here.
That's in the GPv2 order.sol that you're in, which is not the correct one. So if you want to, so for the when importing, it has to you have to specify for the error type you have to specify the. If you go back to stop-loss.sol for a second.
Yeah.
I conditional order not. And that's I'm not sure on that one.
But it should be, because it is the same condition as on the good after time when the time.
Yeah, exactly.
Yeah, so it should be the same. We can read the doc. I found that. I don't know why I didn't. My VS Code seems to be screwed up. But yeah, this error is returned by the get tradable order function if the order condition is not met. And so I think the way that the watchtower is implemented is that if it sees this, it just knows, okay, sleep, try again sooner. It's not yet met. Whereas if we were to revert here, if we actually said like require or like I guess
it's actually like now that I remember, it's that order not valid does indicate to the watchtower that the order may become valid in a future case. It's if the order reverts with proof not auth or order not auth, which happens further back in composable CoW, then the watchtower will strike the conditional order from its monitor.
I see. Cool. And so now we can start actually creating the order that we want to trade in this case. So I can copy this struct. Cell token, byte token are defined. Address 0 here means that the recipient is the same as the sender. So we'll keep the funds in the safe. Theoretically, you could also set a different recipient so that the proceeds of your trade go somewhere else. Data.sell amount we don't yet have, and we will actually get the sell amount from the owner. So it is sell token dot balance of, and then the owner safe. So we check how much does the owner have of the sell token, and that's how much we want to sell. Just exit position completely. Here we might want to actually check that require sell amount larger than 0, right? And even probably some threshold, but
because a 0 amount is a sell amount of 0 is an invalid amount for the back end.
Yeah, correct. And so we now have the sell amount that we want to sell. Buy amount, we said we're okay with any price. So buy amount can also not be 0, unfortunately. That's like a limitation. Like we don't accept, the backend doesn't accept 0 buy amounts, but it can be one way. Seems like a reasonable lower bound. The end time, I see here you've been doing some stuff on like the end time is actually specified in the data. Let's just call this stop loss. Also maybe a remark here, let's keep on the validity. So this is how long should the order be valid. We could just say, current block timestamp plus some value, but that I think has problems if the watchtower then checks block timestamp plus 5 minutes, so it gets an order with it's valid for 5 minutes from when the watchtower queried it, And then when the order actually gets settled, let's say 30 seconds later, the block timestamp might have changed, and then the order that's actually being settled doesn't exactly one-to-one compare with the order that the Watchtower had given. So it's quite important that the order that is returned in getTradeable_order is reproducible within a certain time frame, from when the Watchtower gets it to when the settlement contract actually verifies it on chain. So what I've done here in the past is I've basically just said it's valid for the next 15 minutes and then modulo 15 minutes, so that within a certain time bucket, this value is actually deterministic and doesn't change. I think I have this in here. Yeah, so there's like this current time bucket where I take the current block timestamp divided by data.validity. I guess validity is something in minutes or in seconds. Yeah. But we can just hard code that and say it's valid for 1 week or 1 day. And then, yeah, so we divide it before. That basically makes it so that if it's 3 p.m. right now and we divide it by day, then it actually gets to wait, how did that work? So if the current timestamp is something like, it's 3:58 where I am, and we divide it by the validity, and validity is then, right, we don't get the modulo, we get actually the we get the day that we're currently at, so we get Friday, June 16th.
It just disregards the remainder.
Yeah, and then +1 would be Friday, June 17th. And so, that basically then gives us the time frame. Okay, so that needs to be a little bit adjusted, but that works for the valid 2. So valid 2 will be current block timestamp divided by, does this actually work? 1 day? No,
yeah, it should work. 1 day. Space, yeah.
Okay, let's see when I actually compile.
Actually, I think it'll be like 1 days, which I think is like one of the weird things. Yeah.
Right. Okay, so the valid.
No, go on.
So it would be valid till 0, like midnight, 1 day from now, so basically June 17th, right?
We're gonna have the valid 2. Wait, what do I? Shouldn't it be like divided by 1 days plus 1 day?
Plus, yeah, this is 1 second, right? Yeah, you're right.
Yeah.
Good catch. Okay, so we have the valid 2. It goes here. Then we need to define the app data. App data is basically some more information on the context on the trade. So, for example, if you look at this trade, the app data is actually hashed to a file on IPFS, which stores some meta information. Nice that it doesn't load, but usually maybe we don't pin this file. Let's see. Okay, so here we have a hash that can be looked up on IPFS, and it gives you some meta information, like this order specifically came from CoW from the production environment, had like the slippage tolerance set, and was a market order. And I think we will soon actually stop accepting orders in the backend that have just random hashes set here. So it has to actually be a hash that has a file hosted on IPFS, so that and it can be an empty file. You don't have to give up any meta information if you don't want to, but it actually has to. There has to be some proof that you don't want to encode any meta information in your app data, because we'll use some of that information as a hint to the backend that, for example, you might be willing to wait longer for your order gets settled in order to receive a coincidence of ones, or some other, let's say, meta preferences that are not enforced on the smart contract layer, but that may still be enforced by the protocol. And for that, you actually need to specify a hash that exists. We, of course, pre-upload a bunch of hashes, but this KEKAC stop loss might soon stop working. So we actually, what you can always do, there's actually this encode How do I navigate to this? We have here app data and code, so we can actually write our own app data here. We can say our app code is stop loss. All of this we leave empty, and well, there's one thing. What do we need to actually generate the proper disable order version, order class? It will be a limit order, and so we can now actually copy this is the hash of this app data file. Unfortunately, the UI doesn't allow you to upload it into IPFS, so we would have to upload it to IPFS ourselves. But we can use this hash actually now as a proper hash, so we don't stop using this thing that will soon be unsupported. Do I just do this, or do I need to string it? Oh, this should be fine. And then, yeah, this is the fee. The fee usually has to be set according to a quote that the backend gives us. For market orders, we actually give the user a quote. They then can kind of lock in that fee quote and are guaranteed that their order will exactly cost that much. Now, that doesn't really work for smart contract orders because we don't really have that interaction, that round trip with the backend to query what is the current fee. Luckily, we introduced another order type, which is general purpose limit orders, which allow you to set a zero fee. And if you set a zero fee, you're basically signaling to the protocol that, of course, my order costs a fee. I'm not, our trades are gasless, not feeless. Fees is always taken from the sell token of the user. But I don't want to, I don't want to sign up for a fixed fee. Just take whatever fee you need to take. What the winning solver basically, is still giving me the most surplus, but whatever they need to deduct from my sell token in order to execute my trade at settlement time. So you don't get a predetermined price quote, you get a later determined just in time at the settlement moment fee quote, which would be taken directly from your surplus. But that basically makes it so that we can place these orders without having to worry about having a reliable quote. And it should be a sell order, that's fine. I don't think we want partial fills here. So we just set it to false. And then the balance structs, balance ERC20 is the default one. Let's see if we can easily get the other ones. But basically, we have a few more sources of where the user's balance. So we have a few more sources of where the balance can come from. ERC20 is the default one. External, meaning that this comes from the balancer integration we have from the very early beginning. We were tightly integrated with the balancer V2 vault. And so you can actually use an allowance you set on the balancer V2 vault to route your tokens into the settlement contract. And based on if you want to have external balancer 2 balances or internal balancer 2 balances, you can use those as a source of your funds. In practice, 99.999% of orders will use ERC20, so you don't have to worry too much about the other options, but just if you're a heavy balancer user, you could potentially use your vault allowances and your vault funds here. And I guess this is it, isn't it? Did I forget something?
Nope, this looks okay.
So let's see where my...
Just the one thing, for the practicality of it, when we activated, is that, and this in real life would be that, given that the seller amount isn't really known before time, or may not actually be known before time, so we're using the balance of. In this case, you would have to also make sure you set a sufficiently large allowance to the Vault Relayer contract as well.
We'll set maximum allowance. I think there is actually there is some merit into having a large allowance set from a safe to the settlement contract. In case you break yourself safe, you can still use the allowance you've set in the past to rescue your funds. Which is actually interesting side effect of setting unlimited allowances. But yeah, I mean, depending on your philosophy, you might minimize your exposure and allowances as well. Okay, so let's get to compile. Okay, so
I think I know in 256 declaration, or is it in? No, that's right. Yeah.
Latest price is then defined. Strike price is on data, right? That's the problem here. field on data, and then cell token is also field on data. So this is taking longer. It's a good sign. Maybe. Okay, I think these are some of the warnings that are coming from the dependencies. Oh, here's unused. Okay, yeah, it's basically, we shouldn't call them names if we don't use them. It's fine, it's all lint warnings. They don't seem too relevant for this slide. So of course now you would, before you start deploying and using this, you would build unit tests for it. I think the existing types have actually very nice tests in the repository, don't they? Where are they?
They just below like composable cow base, and then like the one that's like the GAT and the TWAP are pretty
nice. Or even have fuzz testing, right? Yeah. Yeah. So of course, like good practice before, even of course also before deploying, we send to review, to audit and review and all of this. But yeah, here are some examples of how we can write nice tests for them. But just for the purpose of showing, how easy it is to actually get this running, let's skip this very important part, and we're just going to run it on Gertie. So no real funds are going to be at risk. And if I'm not mistaken, we are good to deploy this, right?
Yes, that's fine as is.
Cool. Then we would forge deploy.
Forge create on this one for the contract.
And then it's going to be stop loss, and it's going to have, or for this one I actually have cheat sheet here with commands. So I will use the private key from my one password. And do I need to set the RPC URL? I think so, right?
Yes, you need to set the RPC.
So let's get a free RPC. I guess this one. And dash verify as well, because we want the code to be verified.
Yeah, and also need the Etherscan API key.
I think so. Yesterday when I deployed the base contracts, it was actually fine without the API key.
I think maybe you need quotes around I'm not familiar with the one pass injection.
Yeah, I did it yesterday with environment variables to do that. Okay, so that was set-x private key. And then use that. Wait, and it should be password here, I think. And then set -x Etherscan API key is this. And then we can just take this here. Oh God. And the private key here. And then we should be, hopefully, good to go. And for private key assist is I, of course. Nice, this is a very good error message. Should tell you that error message there.
It's nice that's not leaky.
Unexpected argument, which, what? I did try this way.
It looks like actually set the environment variable as like the literal like OP, etc. Like I don't know if you have to do like quotes. I'm not familiar with the shell that you're specifically using.
Nice. set-x.
Because I think it's mostly because the Twitch session has like a space, and I think that is causing, like the space is causing problems. So if you use a quote.
It's not working. Damn it. Okay, let me create. Maybe how do I do it? I can stop screen sharing and create the. I can just do the deployment. Interesting. Oh, I can figure this out.
Yeah, it may be easier just to like terminate the screen share just temporarily.
And deploy. Yeah.
Yeah, so we can keep things moving and also like preserve our privacy.
Okay, I'm not sharing right now, right?
No.
You are not sharing.
We only see your
Confirm, Alex?
face. I was gonna say we only see your camera,
Okay.
your face, and your office. So someone in the chat is recommending to skip the verification.
We'd also still need the private key as well. For deploying on Go Early. Unfortunately, it's going to be the same problem. So, yeah, it would be nice to skip the verification. Whilst we're doing this, are there any other questions coming in from the community?
No. I mean, I have one. When do we expect this to be fully audited, more or less? Like, when can people start tinkering or?
Sure. This one can be answered. So CoW Grants Committee just ratified a vote yesterday to jointly fund the audit with I forget the name of the audit firm off the top of my head. So that was passed yesterday, and the payment will be going through for that. We expect to get a slot in July, and they have quoted a week's worth of audit time. So realistically, we could expect for this by end of July / maximum like mid August conservatively, like if there's any significant audit findings that need follow up. And then it should be fully audited and good to go. And as well, that is actually the second audit. There has been an internal G0 group audit done, which has resulted in nil significant findings, by only informational type of findings. And we are yet to publish those findings. But if you have a look through the GitHub repositories, there are commits addressing audit findings in there.
Nice. So, let's see. Hopefully, a lot of teams will start playing with it.
There's a lot of stuff we can do with this, absolutely, especially like with once we have from the back end like pre and post interactions as well. Like it starts to really open the door as to like what we can do in terms of opportunity with this.
Cool, we're getting there. I have the contract uploaded, just not yet verified. The verification we can, worst case, also do in the browser.
Did you want me to set a value on the static oracle?
Let's do all of it. Is this a permission one? Like, are you are you only able to set it?
No, it's completely public.
Okay, cool. Then we can just do it together. Okay, I think I can start screen sharing again. Okay.
Yeah, now we see your code editor.
Okay, cool. So the smart contract was actually deployed. Where did it go? Here, stop loss. Okay. So this is the address where it's deployed. Let's maybe bookmark it just in case we forget. And this is the code that we just wrote. And now we will start configuring our safe first and foremost to be able to use the composable CoW framework and then instantiate one of those orders. So the way that we do this is we have here a vanilla safe created where I'm the only owner. Of course, you can have like more complex owner structures, but for simplicity, we use this. Now, the first thing we need to do is we need to set the extensible fallback handler correctly, right?
Correct. Set fallback handler on the safe.
Do you happen to have the? Can you send me the? Do you happen to have the deployment address, or do I need to look?
I see just to the left of your current tab, you have the R&D Labs composable CoW repo. Left of your current active tab.
Yeah.
Yep.
And here I have the pull request from yesterday, right?
Yeah, pull request. Yeah.
Okay. This one contains. It doesn't have the fallback handler though, right?
Oh yeah, correct. Sorry, 1 moment. I'll dig that up out of. Very good point. Okay.
But I mean, I can just check who deployed this and they deployed the same.
I sent it to you in the chat.
Okay.
In GT.
Nice. Okay. So let's this curly. Yeah. So this is a deployment of the extensible fallback handler that we discussed. So this is the thing that I first need to configure my safe with, so that my safe can speak different implementations of EIP1271. This transaction is, somewhat, risky in that you should really trust the fallback handler that you're setting on your safe. If you set bad fallback handler on your safe, that can potentially have access to all your funds. And so it's very important to make sure that the extensible fallback handler, or that whatever fallback handler you set, doesn't have any bugs. That's why we've gone through 2 audits. We've worked with the safe team, a lot of review, and we'll also now, of course, consider this as part of the bug bounty program. But yeah, just as a word of caution, setting your fallback handler safe is a important step, or is a big thing. This was the address, right? No. This was the address, right? Yeah, it's the address of my safe. Okay. So yeah, I'm setting the fallback handler to extensible CoW. I can simulate, of course. Just assume it works. And then the next thing I need to do is configure composable CoW to be the responder for whenever there's an EIP1271 signature on the domain of CoWSwap. Right?
Sorry, I was just tapping between. Yes. So for this one, is you have to call the safe itself.
Yeah, but with the ABI of the extensible fallback handler.
That's correct.
All right. Okay, so let's get the ABI from Etherscan here. Load it here, and then we can actually set domain verifier, and we set the domain verifier to the that is the GP Here we
the domain verifier is set to composable CoW, and the domain is set to the GPv2 settlement domain separator.
Right. Okay, so I'm getting the GPv2 domain separator from the settlement contract. So this is the main GPv2 contract. You have to check that you're on the right network because the network is part of the domain separator. So that differs on mainnet from Gurley, even though the contract is on the same address. So we are setting the domain separator to be the domain separator from the protocol we want to enable here. So this is CoW protocol. And then the verifier is going to be composable CoW. And if I'm not mistaken, this is composable CoW. So this is the address we want to set here. Create batch, send batch. Let's go. And okay. And maybe just to reiterate what we had in the beginning on the infrastructure side, we have now taken our vanilla safe, which comes with a default fallback handler, replaced it with the extensible fallback handler. So we can now have a different fallback handler for each domain, and then we configured composable CoW to be the is-valid signature implementation for that domain. Now that doesn't do anything in and of itself because we haven't actually created any conditional order yet. So any is-valid signature call to composable CoW would just say, no, I don't want to trade because you haven't given me anything to trade yet. And so this is what we'll do as a next step. We'll actually create a composable CoW, a stop-loss order there.
Sure.
Let me clean up a little bit here on the tabs. So this is stop-loss, this is useful, this is not useful, composable CoW. Okay, so basically we want to call the stop-loss, and we want to call composable CoW, right? Create order on composable CoW. Doesn't find. Why doesn't it find the ABI? No.
This is for composable CoW. Yeah, it should.
It should.
Not that it helps.
Just copy it manually. And so we want to create an order here. And so now what we need to do is we need to encode the data struct that we've defined. So we need to, not even this one, we need to encode a
So it's going to be the tuple of the address of the stop loss contract. Then it's going to be a salt, which we can just insert something random there. And then for the byte, it's going to be the ABI encoded data struct.
Nice. Okay, so we will have to create that. I think there's a website for it. How does this work in the safe? Curly with rectangular brackets, maybe. So the address is the address of the handler. The handler is stop loss, right? We want to place a stop loss order.
Mm-hmm.
The salt can be anything, so we can just give it at some unique value, right?
And then the ABI encoded. Wait, generally, I personally use like Forge and Chisel to do this stuff.
What is it? There's a cast, or how would you do it? Teach me.
Because like you can actually like have you used Chisel before?
I don't think so. Yesterday I used.
Because like Chisel should be installed by default as well. If you use Foundry up, and Chisel allows you to do basically Solidity scripting, and so you can create Solidity and output like straight to a terminal, as an example. But not necessarily for this one.
I mean, how do you spell it? I have.
CHISL.
CHIS. Okay, Chisel.
Yeah, and enter, and that gives you that's essentially now a Solidity prompt, and so you can just type Solidity.
So ABI.encode and basically
The thing is, like, you'd have to like also define the structs for I conditional order params, which is going to be what is bytes or what is ABI encoded and passed in for the static input. But
So-
yeah, so the sorry, go on.
You want me to go to composable cow? Like, walk me through the exact process here.
Okay, so we're doing a create, and the what's just back up to create.
Let's actually make this one bigger. Okay.
Okay, so that's with context. Back to the one above, the previous. Yeah. Okay, so we need to pass in. So during the create, the tuple that we need to do is the conditional order params, and so we need to be able to ABI encode this. Now, to the audience, there is a forthcoming SDK that's going to obviously make this a lot easier, because it's a lot of heavy lifting to do this all manually at the moment. So we need to define the I conditional order params. So you can actually just go to the I conditional order interface, and you can pull the struct from there and actually declare the struct straight away in Chisel.
Like this.
So you can copy that. Yep, and then get rid of the ABI encode. Struct.
This is an address, right?
Yeah, it's an address. That's correct. Okay, so we've got the struct defined. Now we can actually just straight away. You can, if you want, you could define. You could allocate it to memory. So you can go conditional order params, memory space order, as an example. And then go equals, and then it's going to be the conditional order params, and pass in the handler salt, and then it'll be well, actually, before we do this, like, we should also define the struct for the data that was used in stoploss as well. Sorry.
Right.
Yeah. So that we get
here.
Yep. And that's just address. And the IERC20 as well, address.
Cool. Okay.
So now you can define the data that we want to use. So data memory.
Memory data equals okay.
And then
cell token. Let's do. We have wet, right? So okay, let's check out this. Save. It has. Why does it not realize that it has width? No, I did. Wait, this is the right contract.
Can you send me your contract address?
I actually have it here. B4 is width on Gertie. I can send you this one. Yeah.
Okay, cool.
But I have width now, so
okay, cool.
This is B4, and then let's get die, and for die I'll just use what my account traded earlier. Was token transfers. This. Okay, this is what is die currently, and then strike price. Let's say whatever. What is the price of it right now? 1661. So let's do a 1600 strike price.
Okay.
And then it needs, how many decimals did we say? We said we are at, I guess.
Well, we said that we can just set it as as whatever you want arbitrarily. So because like we can set the the price that is put out by the example price oracle.
And you said default is eight decimals, right?
Yeah, but like we don't have to specify it necessarily, so we can just specify like
1600
decimals. 1600.
Okay.
Yeah, it's fine.
0 decimals, nice. And then you had the example oracle that we are going to use is this one. So we now have defined the order. We want to sell B for FB, WEF for 0xDC31 die if the oracle says 1600 or less, and the oracle we are using is this address.
1 moment. Flipping between screens. Okay, and by the way, in terms of like different for the data, you have to define. Yeah, so like data brackets, and then it'd be like curly brace from memory. Data brackets. So bracket and as in like bracket, and then curly brace. And then it'll be the fields. So that would define sell token, buy token.
Wait, this doesn't work.
Oh no, sorry. Sorry.
So now I want to ABI encode this, right? Decode. No, encode. Yeah.
Yep, encode.
And encode works. It's data, data like this.
It should.
No, it's the other way.
It should just be data. Like no need to specify.
Because it does.
Yeah.
Okay, nice.
So in which case, you should, but we don't necessarily need to do this because we can pass ABI.encode into the struct for conditional order params.
Right. Okay. So conditional order params. Okay. So we have that. And then we say conditional order params memory params equals conditional order params. And the handler we said, I'm gone here on this one, but the handler we said is going to be stop loss.
Mm-hmm.
The salt we just wanted to leave kind of random, and the static input is ABI.encode data. This doesn't because it needs to be like bytes 32. Right. Why does that work from int console byte 32?
Sorry, one moment.
It works with 0. We just have a 0. 0 salt.
I'm just setting the oracle to like 1800 or something at the moment, so it doesn't trigger straight away.
Yeah. Okay, so I think we have the encoded data.
Okay, back to yep. Okay, so we've got so for the contents, and okay now. So that is the okay. It'll be back to the safe as to.
So uncomposable CoW. ABI is still not working. Maybe it's because no. It's fine. Okay, create. It's interesting that it says it's a double here, but we actually encoded it, but it's
yeah. But it's we did encode it, but I forget how to define the tuple in safe interface for that. Because usually I just do all this by skipping.
I think you actually define the individual values here in an array like this, and so we actually need to ABI encode data. is it like this?
So I actually don't know if the 0x0 needs to be also if it
32.
needs like a full bytes 32, like for the salt, like with the way it's interpreting the data.
Okay, let's just take a transaction hash of the creation of the stateless contract. Nope. So the expected comma after array element. Maybe it needs. Yes, there we go.
Oh, nice.
Okay, so you need to put the hex strings into apostrophes and then commas, and then you have your tuple. Okay.
Okay.
So we have the handler, we have a salt, and then we have our encoded struct of the subclass order. And now we want to dispatch true. This basically means you're telling the watchtower to start querying this order that's being created, right? Like the watchtower will then continuously check, is the stop loss order triggered? Yes or no, yes or no. And if it's triggered, it will tell the API to incorporate it. So if we create this transaction, oh wow, this is new. How did this just come up? Can use this cool.
By the way, just a quick question. Are you still running the before you are you still running the Web3 actions in the 10.e stack?
I don't think so. Not on Girly. I think we ran it on this composable CoW. Maybe though. Are you running them?
No, I'm not running them at the moment, so I was just about to start them.
We can replay the transaction.
Replay the transaction. Yeah, that's fine. Can you send me the transaction hash?
I just feel like we need the node. I need to set the node URL. This is the only secret I need, right? So I need to set node URL 5. Or you wanna run it? You wanna run the watchdog?
I'm running them now. Wait, it's okay. So just intendly.
Maybe just for the viewers. So when I said dispatch, this will tell the watchtower to start tracking these orders. We actually have an ongoing grant with Autolanas to build a decentralized watchtower that can be run kind of across hosts in a peer-to-peer network. So you as a smart contract developer don't necessarily have to run it, but you can if you want to make sure that your contracts are being tracked. Right now, we have implemented those as Tenderly Web3 actions, which are actually a very handy and practical way of watching stake on chain and then having a hook, just a JavaScript code that gets executed whenever something happens on chain. But we are moving to a more, I guess, decentralized model. But yeah, theoretically, these watchtowers can be run by anyone. There's no permission, and we'll provide a, I guess, network provide some form of infrastructure so that you as a developer can make sure that these watchtowers are running and picking up orders.
But can
sorry. No, I was gonna say, but currently there's no documentation available yet, right?
So the code for the Tenderly Web3 action, which you can run your own Tenderly account, is actually checked into composable CoW. So this is the code for the watchtower. Quite straightforward.
Sorry, Felix, can you also send me the TX hash for the transaction that was mined on the safe?
Yes.
Please.
This one. Logs. Let's just check that conditional order created. Yeah. So this is the transaction that dispatches the order, and this is the event that triggers basically the watchtower to index it. I'll just send it to you.
Thank you.
And yeah, just for the documentation, so we are, I think Monday we are supposed to receive the first deliverable of the team that's building the decentralized watchtower. So we have actually not a lot of effort into documenting the Tenderly based one. It works fine. It works, nicely. You can run it. It should be documented. Watchtower. So basically, you run Tenderly actions deploy. This is kind of what you need to run to deploy the Watchtower locally if you have a Tenderly account. And then it will just wait for these events, these conditional order create events. This way, it knows exactly what to look out for. So it has like the static input, and basically will just keep track of all the orders that have been created, and then constantly poll, is this order tradable now? Is this order tradable? And as soon as it is, tell the backend about it.
Okay, thank you for that.
If we want, maybe actually, I wonder, maybe it's better in case something goes wrong, we can also debug it on screen. Maybe it's better if I actually.
Yeah, possibly. I was just checking that like it has picked it up. It has indexed it. I just haven't seen it hit yet again on the watch. But yeah, like if you want, the only thing that needs to be set for the Tenderly actions in the secrets is node underscore URL underscore 5. And then with that, with the RPC for Burley, then you can start Web3 action and then manual trigger on the TX hash, and I can disable my actions.
And we had the URL endpoint. Maybe not the best one. Should use your own one, but just in order to not have to worry about secrets again, let's use this one for now. And then I guess you're saying actions, watch order. Here I can basically use manual trigger network girly and block.
Yeah, and it's definitely the actions are definitely triggering. So yeah, it's
copy on write.
Oh,
I need the block number in here, right? Okay, so this is the block number that this transaction was on.
No, you want to one moment. So just going back to the screen. So with the Web3 actions, you have them all deployed. So it's. Can you just show me the watch orders? I think I don't know if you deployed the latest version.
I need to register. Okay.
Yeah, it's in register single order. Yeah.
Okay. Right. Manual trigger. Okay, and that's based on TX hash. Right, because this one is based on events.
Yeah, and the other one polls like for get tradable order.
Okay, so this is the payload, and then I copy on. No, I write. No,
Yep.
I copy and write. Doesn't matter.
Right.
We could push start.
Right, because you'll need to adjust the storage for the block monitor.
Will not modify. Yeah. Okay. Trigger. Submitted. Execution's updated, and okay. So now this was the amount of orders that we tracked before, and now we have added conditional order. These are the parameters of the conditional order to already existing contract 0x94. So it was maybe already running.
Yeah, maybe it was already running actually.
Okay. And then you were saying to check that it's actually watching orders. We go into the execution history. Can I filter by? Problem here is that it runs all of them and not just the one on network 5.
Well,
okay,
that's got it right there actually.
Call exception.
Which one is that accepting on? Because like the check-in params like the 0x53.
Yeah.
What was the handler again for the stop loss?
It's the stop loss, the contract that we deployed.
Yeah, so it is 0x53.
Yeah.
Okay.
I mean, it's fine to be reverting right now, right?
Yeah.
Just,
But it looks like
I think
it looks like there might actually be like what just as a piece of advice, like maybe actually torch the storage in Tenderly to reset it and then manually trigger it, just in case like you have like some, because like when I was just looking at my Web3 actions, I wasn't getting any reverts. So it looks like there might be some weird little bug in there. So in storage,
you want me to just purge this completely?
Possibly. See how it goes.
We're gonna test it. That's why.
Actually, the conditional order registry one, because I can't remember if it has any issues associated with like a zero set. So in the storage, you see like conditional order registry one. It's got like a map. So if you go view value on the conditional order registry, and then copy that.
Okay.
And then put it into 5.
Okay. And then we run again the register single order on the. This was this fetch payload right trigger. And so, but you know, what could be the problem is that we actually need a geth node, and the one that I've configured might not be a geth node, right? Like
Sure, yes. No,
so it's actually it matters. It matters which one I'm using here. And Anchor might not be using the using geth. Okay, but let's check if that's the case. So this one was now processed, and so on watch orders, if I actually see the execution history, then this one is network 100, this one is network. Right. Network 1 fails, okay. Actually, let me remove the 100.
This is the problem with going through the penalty actions. It
doesn't let you filter on.
Would be nice.
Does it only used?
Here,
okay.
Got it?
Yeah, okay. But here it's the same problem. It says call exception, and I think this is because it's
for those in the audience, it's related to when the call reverts. Some RPCs don't return the actual reversion error correctly, which is then checked by it's an existing ithers problem where the RPC returns essentially an invalid transaction. Well, it doesn't properly return the reversion.
Okay, so this works. And now, because it got purged, I need to rerun the registration.
I don't know if it actually got purged. I don't, because you can see in the storage if it got purged or not. I think it just reverts. Like it just fails out. No, actually, yeah, it's purged. Okay.
That was the problem. That's why when I was testing it.
Sure.
So register single order main trigger girly. Maybe I should actually invest in taking the transaction hash here. This was the one, right? Yeah.
Mm-hmm.
Okay, submitted. And then we now have it in storage. Yep, so it's back in storage, and hopefully on watch order we can now see it being picked up. Execution history, 105. No. Infura is using guests. Like, and maybe did you use the tenderly ones? Which ones?
Wait, because the actual RPC that I'm using, and which was picking up and querying. From memory, I do use the tenderly. Oh, actually no. I think I might actually use Pocket for their relay.
It's not. If you have the link that you're using where it was working, then it doesn't contain a secret. You can maybe send it to me.
Yeah. What's 1 moment?
Good. I'll try one more time with that tenderly one. Yeah, that's why outsourcing this work, because it's actually the infrastructure right now is a bit brittle.
I just put another girly RPC in the Jitsi chat if you need it.
Okay, let's check this one works.
Still the same.
Transaction. Okay. Can I use yours, or does it contain a secret?
Wait. It does contain a secret, but I can just launch it. It doesn't matter.
Okay, let's do that. It's too late. Copy. So now we replay one more time. This is the hash. Okay, it's been added. Watch orders, execution history, submitted. Same thing.
Same thing?
Do you want to just run it on your end? Maybe it might actually be that
Yeah, I'll see. I'll check. I'm pretty sure it was.
Okay. Actually, let me do another thing. What we can do actually, on the watch, we can just not purge, right? Okay, I'll just change the code to. Can I do that easily? But then I need to upload it to Tenderly. It's not super easy. The problem is that basically, whenever the get trade order fails, it completely removes the order from tracking, so it stops tracking it. Do you want to test on your end if it does the same?
Yeah. Just one moment. I'll just because it's already registered in my actions. I'll just double check that it's in there. I think it's purging on mine as well, by the looks of it. Yeah.
Do you have an easy way, because you might not be sharing screen there, to just inside watch to remove the purge logic and just say if it reverts, don't purge?
Yeah. Just one moment. Actions in watch.
Check. So actually in the catch, just the delete, it's line 171, 170.
171, got it. Okay, did you want to redeploy the tenderly actions on your end, or?
I'd rather not, because I haven't set it up
Okay.
on this console, so it might take some time.
Yeah.
I will actually stop it. Here, stop all. And then they can run on your end.
Done. Print on field orders, conditional tweets. Okay. Just building the point now.
Nice. And so yeah, I can start preparing the rest of the demo. I guess so. Right now the Oracle is set to 1,800, and so we'll write the Oracle to be somewhere below 1,600 once we know that the Watchtower has picked up the order and is working, and then we should be seeing our save automatically placing an order basically as the Oracle updates without us doing any interactions on the save, which we see in order being placed.
Just tenderly's deploying.
Yeah, perfect.
It'd be nice when so you said like the delivery for the first delivery for the decentralized Watchtower is due Monday.
19th. Yeah.
Nice. So for those in the audience, it means that you don't have to go through this, and it should be handled autonomously.
Exactly. Yeah. So this part of the thing that we're doing there really is not needed. Really, all you need is write the contract, deploy it, and then dispatch the order. The rest will happen under the hood.
And back, grab the event, replay it. Okay. So the new version is up and running. It's executing. Just checking for the GUI. Yep, so it's going through, checking. Just checking to make sure it indexes correctly.
Basically, it might, depending on if you remove the error message, it might still say that it's purging, and
yeah,
it shouldn't actually purge.
Yeah, it was just making sure that the I'm just checking for it to see to make sure it's actually indexed the order. Yeah, I see it's indexed the order, checking. Yeah, okay, got it.
Cool. Then let's I'll manipulate the Oracle. Of course, this wouldn't happen in real life. The Oracle would update itself, but here we can control the Oracle. So I'm going to set the price to 1,500. And when this transaction mines, we should see the Watchtower basically picking up the safe order and placing the safe order in the system.
Fingers crossed.
Yeah. So I think we have right now the Watchtower has a delay. It only queries once per minute or so. So there's a little bit of a delay. The Watchtower that we're working on will actually run every block.
Open the door.
Moment of suspense. Did it?
Okay, wait, I see
actually work.
Oh, yes, I think it may have.
Okay, maybe I'm just on the wrong.
It should be that order UID that I just pasted. Should be, but it did come back throwing an error.
So you know what the error is? Okay. Actually, this is something I wanted to do and show the listeners or the yes, because it's the thing that I always do incorrectly, and one thing we should give a better error message in this case. But before the smart order can trade on behalf of your safe, you also need to set allowance for it to be able to trade. Otherwise, the smart contract cannot take funds from you. And here we have the WETH contract. It currently doesn't have allowance. We go on CoW, use the safe app, open the tokens page, and then we set allowance for WETH. Very good point. And we can use this code relayer functionality that the safe now has, that we don't even have to execute the transactions ourselves. And with that, once that is mined.
And that perfectly explains the API error that was visible on the watchtower that was being thrown.
That shouldn't be a purge of a reason.
Yeah, it wasn't a reason for purge. So it wasn't the reason I was purging, but it went and found the order, then tried to submit, and then it reverted with a HTTP error, which was the API error that was thrown back.
It's still in the system, right? That didn't get purged. No.
Yeah, it should still be in the system. Just one moment, I'll quickly check.
Yeah, this is actually something we need to find a way to make very clear for the user that they have to set the allowance, because otherwise you create a stop loss order. You think your funds are safe in a crash situation, and then if you haven't set the allowance, it's actually not. So maybe having a way of simulating how if your order will go through under certain circumstances might be nice. Do we have?
I think there might actually be a JSON error in the just having a look. Just one moment. I'll try one more thing.
Famous live demo. Did it find the order again and try to place it, or was it was it not finding it?
Oh, sorry. Back to you. I was on mute. I think there might be in the state within my storage, the storage within the tender action, the JSON was getting encoded incorrectly for some reason and creating a circular JSON file, and wasn't attempting to create a circular JSON file and was throwing some weird and wonderful errors.
Okay.
But I've just attempted to purge the states to create a new one. Yeah, so I can just for the viewers, I can paste in the channel. This is what I'm getting at the moment. Sorry, there's some weird and one thing's happening there.
Don't worry, technicalities of live streams.
Yeah, exactly.
So, but now are you replaying the register?
So I have replayed the register, and it does go to trigger the order, and then it fails at the point of serializing data. So I can actually see it goes through, recognizes that there is an order, and then tries to place it.
Okay. Did I think what actually might have happened here is that we added the context to the get tradable order method, and we didn't update the watchtower for it, or did you?
This is true. One moment. Conditional orders has.
Oh, but it's not needed on the main on the top level.
Yeah. It's not needed on get tradable order with signature.
Okay. Let me try one more time to restart my actions. And I'll start all. And then if it doesn't work, we'll have to leave without the live demo.
Restart it.
Register single order. Okay, man trigger girly. Okay, this one goes through, and then watch orders. Is interesting. Yes, we have the same problem here
with the trying to serialize.
Yes. This thing is the problem, right?
Which
the type number hex.
Wait, I was having a look at that. Wait, that should be fine because that's just a standard. It's managed to obviously do that, but then when it comes to, I'm just having a look inside place order and the functionality with inside place order, and
it's not my normal. No, doesn't exist the order. I mean, if we have the correct struct, we can just place it api.cow.phi/docs. We can just place it here live. We can just do what Watchtower does, but manually. Maybe that's
yeah.
So let's do that. So we post order to, first of all, not mainnet, but to girly. Try it out. And so the cell token is this one. The byte token is this one. The receiver is this one. The cell amount is this one.
It's going to be AFK for a couple minutes.
Okay. The buy amount is 1, valid 2. Oh, interesting. Actually, valid2 that's screwed up. Interesting, that's the problem. This is app data. Fee false. Okay. Interesting. Where is valid2 screwed up? Oh, because I forgot to multiply bits. Not really. This is the number of days times the days and plus 1 days, I guess. And then, damn it, can I run this again easily? Okay, let me just quickly redeploy. Oh god, this is gonna take some time. It's 15. Let me do that just for completeness. I kind of want to get it running. I'm just going to quickly stop sharing my screen. And am I? Yeah, I'm no longer sharing.
Now we can only see you now, so we can.
Okay, cool.
Back.
Yeah, I think I've found the problem. It had something to do with the way that we computed the time. I'm just redeploying right now.
Oh, so there's a problem in the actual contract.
Yeah.
Okay.
Okay. So we have the new contract available here. And it is verified. Yes. Okay, so I can close this window and start sharing again. Okay. So basically now we have to go through the order placement again. But that was fairly straightforward. we basically use the composable CoW. Where do we have composable CoW? Just get the transaction builder here. This was composable CoW. New transaction. It still doesn't find the API. So it creates an order, and we said we need the handler, and the handler is now the new stop loss. Well. You're right. So square bracket, then the salt. Again, we'll just use some transaction hash. And then the encoded data is just what we didn't change. And dispatch should be true. Create batch, send batch, submit. And so, yeah, maybe because you were offline, the problem here was I didn't multiply by days. I just took basically the stripped of the number of days and then just plus 1 day. So it was valid until 1 day after Unix timestamp starts.
Sure.
So that was unfortunate. Okay, now actually I think our demo is a little bit screwed because we're not actually manipulating the price afterwards. So the order has triggered actually immediately. You can see it was placed, and because the oracle was below 1600, it immediately triggered. But now we can see the order was picked up by the watchtower. It was placed in the system. It is selling a lot of weth for DAI, and yeah, ideally this will be settled in the next couple of seconds. But yeah, we now actually, because the oracle had already triggered the strike price, as soon as the order got placed, it became immediately executable. So nice.
You think it most wouldn't be that hard for us to I can tweak the oracle back higher, and then we can actually do it
one more time.
Yeah.
Sure.
We come this far, let's go for the end.
Okay, let me just swap back into. I need to swap back now into weth. I'll let you do the oracle, and it's not ETH weth. Fees exceed amount. Okay, proof die and swap. This is a really cool new feature that we have, where if you trade a token for the first time, you don't have to approve and then swap. It is now just one transaction. So as a safe user, you can do in one click. You can do approve and swap.
Okay, the state has been set back to 1800.
Okay, so then let me go ahead and place the order again. So we will create a new stop loss order. The value here are still for the stop loss handler. It's this one. As a salt, we now need to use a different salt because everything else would be the same, right? Like the orders would clash if we did use a different salt. So let's maybe use just the transaction hash of the previous.
Just thinking as well, you might want to slightly trim the. I don't know if your balance will end up the same, because if your balance is the same, it could likely result still in an order UID collision.
It's not the same because we lost some on trading way back.
Sweet.
Okay, so I have the stop loss handler. I have a new salt, and then we'll use the same payload. This was the payload. We will dispatch true, and we'll send this transaction. One more transaction left is ours, so this has to be the right one. On the relay. And then, cool. So as this one gets executed, we will then not see it immediately in the order list, because now the price of ETH has recovered. We're at 1800 again. Okay, this one just has been placed. Just in mind. Yep. Okay. As you can see back in our UI, in the orders page, we have our original sell WETH for DAI, and then we have the trade that I just made from the UI selling back our DAI into WETH. So now we have about we have 0.39 WETH in our settlement contract, and we have a ongoing stop loss order that says as soon as ETH goes below 1600, sell everything. So let's go to the Oracle. Which one is the Oracle?
In the
it's here. It's here. Yep. Just double checking that it's currently set to 1800. Yep, 1800. So now when I write it to what we said, 1500, then as this transaction gets confirmed, we should, as soon as the Oracle hits, see the smart contract placing an order by itself. Let's first wait for the transaction to mine. It's not yet mined.
Damn.
Pending.
Look at that surplus.
Yeah, because we have zero expected out amount. So it's very high. Guess I was cheap on gas here.
It's because Solver's optimized very well, Felix.
Yeah. Okay. The Oracle price change has been mined, and then it can only be a matter of time until we see our order being placed. There we go. So now the order is in the books, selling all our WETH for DAI at fire sale prices. It's open, and solvers will now pick it up and settle it. And here we are with a little bit of a struggle, but the root cause was actually me not writing a proper code for computing the valid to timestamp, which would have been caught if we had written some unit tests and some basic sanity checks. So it was a bit of a due to the rushed development here. But yeah,
we still got there. All good.
Yeah.
Nice.
Now let's wait for this order to fill, and then I guess if there's any more questions, I looked a little bit at the chat. Seems to be no immediate questions. Again, we are in Discord. There we go. Look at this surface. We are on Discord. Happy to answer more questions. Also, we'll probably release some more information on the Watchtower, how to become potentially a member of the Watchtower network, to also contribute if you are running your own smart contracts. You might want to have just on your dev node or some other piece of infrastructure, one of these things running. But yeah, the key takeaway, let's maybe summarize a little bit what we did today, was we've basically written, 50 lines of Solidity code. Do it properly, you would probably add another 50 or 100 lines, write proper unit tests, but we've, in very, very limited amount of time and space, we actually written a complex order type, a stop-loss order on top of CoW protocol. We've deployed this order. We started from a new safe, configured the safe to use this order type as its implementation of EIP1271, and then showed how without any active interaction from the smart contract or from our end, orders can get placed in the system if the circumstances of the chain change. If the Oracle price changes, the smart contract decides it wants to trade, and it trades autonomously on your behalf. And so yeah, I think it's a really powerful tool and framework. We talked a little bit about potential use cases, but really I think the main takeaway is here it's up to your imagination where to take these type of orders, and really I think at ECC and maybe at some other venues we'll try to put up bounties on the most creative and most innovative smart order types. And yeah, we're hoping to unleash a couple of new trading paradigms on top of CoW protocol using this technology. I don't know, MFW, do you want to say something, and then I'll hand it off to Master CoW to end the stream.
I think that you summarize it quite well. Basically, with the design of the architecture, you can do, so what we've done here only demonstrates the use of a static or known input prior to the creation of an order type. With the architecture, you can have known data at order creation time. You can also simultaneously have data that is known at order creation mining time, as well as providing dynamic data off-chain, which can then be validated in all types of wonderful ways that you can, whatever you can think of. And if anyone has any improvements, ideas for how we can increase the scope, which by all means do reach out to us on Discord as well.
Awesome. Thanks so much, MW, for coming online and hacking with me. Really cool contribution. The extensible fallback handler beyond CoW I think will be very useful for the ecosystem. So to get a bit more, nudge the ecosystem to build that faith into adopting that handler. But I think it's really unlocking a ton of use cases beyond just CoW protocol. Alex, do you wanna close out for us?
Yeah, well, no, thank you everyone who joined us. Very excited to see the different features that are going to come out of this, and definitely join our Discord. It's discord.gg/protocol. And with that, happy weekend, everyone. Thank you especially to you, Felix and FW, for doing this live coding session and going through the live hurdles of demos.
live debugging, yeah.
It was great.
Thank you. Have a good weekend.
Bye everyone.
Bye.